Hello, welcome to today's lecture. Very well, we're going to continue chapter 14.2, limits and continuity. Guys, Math 1D is dependent on Math 1A. When we're talking about limits and continuity of functions, you're actually getting back to functions in one variable. So if you don't remember those limits, those techniques, the continuity, I suggest you to get back to your 1A notes, review the examples, review definitions. I feel comfortable about those. I wrote down some of them for you on page 11 and 12. For example, you can find the definition of limit. You can find the infinite limit, limit at infinity, right-hand side, the left-hand side limit. And in general, we say that a function has a limit if a limit from left-hand side is the same as the limit from right-hand side. Otherwise, we say that the limit doesn't exist. There are some properties to find the limit of a function. For example, if you find the limit of c times function, c is a constant, you can write it as c times the limit of the function itself. Then you have addition and subtraction of two functions. You can just find the limits of those two functions, add and subtract them. The same for multiplication. For rational function or division, you need to be careful about the denominator of the function. If the denominator is 0, it means that you have to make some adjustments to the function. Then a limit of a function raised to an exponent like n, be careful here, n is a positive exponent. If it's negative, it means that your function is going to be on the denominator and it cannot be 0. Is going to be the limit of the function, then raise that number to n. And finally, limit of square root function is the same as square root of limit of the function. Here we have limit of exponential function. Here we have limit of ln function, and so on. On the next page, page 12, we have more techniques. For example, if you have a function and it is just a nice and continuous function, it means that the limit of the function at any point is the same as the value of the function, outcome of the function, when you plug in that number. We have also some nice rules to find the limit of functions when it comes to rational functions. For example, if you plug in a into the functions and you get 0 over 0 or infinity over infinity, what you can do, you can just take the derivative of the numerator, derivative of the denominator, and take the limit of those derivatives. And again, if you have 0 over 0 or infinity over infinity, you can take the second derivative and you can continue the process. There are many techniques to get rid of common factors. For example, if you have common factor x minus 2 that makes the function 0 over 0, other than using L'Hopital's rule, you can just factor out the numerator, factor out the denominator, and get rid of common factor. For radical functions, you can use the conjugate of the numerator or the conjugate of the denominator, whichever is working for you. In that question, then simplify the function and find the limit. We have piecewise defined functions defined on a finite numbers of interval, and the limit of the function, depending on which interval you're working on, can be found. And for a combination of functions, the same. Some nice continuous functions. As you remember, any polynomial function is going to be continuous. For rational functions, you just need to be careful about the denominator, zeros of the denominator. Then you have root functions, and the index is odd. It means that the function is continuous everywhere. If the index is even, like square root, fourth root, sixth root, you should be careful about the radicand or the quantity inside the radical. You must set it greater than or equal to 0. For exponential function, e to the x, function is always continuous. For ln function, you should be careful about the domain of the function. X cannot be negative or 0. For trig functions, cosine and sine, it's continuous everywhere, tangent and secant. These functions can be written as rational functions, so you should be careful about the denominators or vertical asymptotes for those functions. And we have one important intermediate value theorem, which says for any continuous function on a closed interval a and b, if m is a number in the range of the function sandwiched between f of a and f of b, you can always find a value in the domain like c such that f of c is equal to m. Now, what if we have a function in two independent variables, f of x and y? In this case, to find the limit of the function, we're working with different paths. What's the meaning of that? It means that you have to take paths or ways that passing through the point A and B, then evaluate the function if on different paths the function has different limits. It means that the function has no limit at that point. But if the limits are the same, it means that the function has a limit at that point. Remember that for some nice functions, like polynomial functions, these functions are always continuous everywhere. So the limit exists and it is equal to the value of the function at that point. Very well, let us go over some examples to feel comfortable about this topic. Here you have a polynomial function in two variables, and the question says find the limit of this polynomial function when x goes to 1 and y goes to 2. Remember that for polynomial functions, nice functions, you shouldn't be worried about anything. You just plug in the values and find the limit of the function. Please pause the video. Try to solve this question, then we go over the solution together. Very well, by plugging these two values into the function, here the outcome of the function is going to be 11. What's the meaning of that? It means that the limit of this polynomial function when x and y goes to 1 and 2 is equal to 11. Very well. I expect you to ask, what if we don't have a polynomial function? What would be the next step? So for functions other than polynomials, you have to use different paths. For example, you can take y equal to 0 as x-axis. You can use line x equal to 0, or y-axis. You can use a line y equals to x, or you can work with more general paths like y equals to mx, y equals to mx squared, y equals to mx cubed, any function passing through the origin. Note that after simplifying the function using any general function like y equals to mx, y equals to mx squared, y equals to mx cubed, and so on, if the final expression includes only m or any expression involving m without any x or y, then you say that the limit doesn't exist. Why is that? Because the limit depends on m, and you can plug in any random number for m. Example, show that the limit doesn't exist. Please take a minute or two, solve this question, then we go over the solution together. Very well, let's go over the solution together. Here you have a rational function. Okay, you might say, very well, I want to check different paths and see if the function gives me different limits. The first path you can take is y equals to 0, which is nothing but x-axis. It means that wherever you see y, you just write down 0. Okay, after simplifying the function, the outcome is equal to 1. Note that your x cannot be 0. You're approaching to 0. So what's the meaning of that? It means that as I walk along path x-axis or y equal to 0, the limit of the function is getting closer and closer to 1. Let us check a different path. Let us use y-axis. or line x equal to 0, it means that wherever you see x, you just write 0. After simplifying the function, the outcome is -1. So what's the meaning of that? It means that as you walk along line x equal to 0, function is getting closer and closer to -1. Here you can stop and say that since 1 and -1 are different, so the function has no limit at the origin. Let us take a look at another example. Here you have function f of x and y equals to xy divided by x squared plus y squared. Does the limit exist at the origin? Please pause the video, try to solve this question, then we go over the solution together. Very well, let's use the shortcut. Let us use path y equals to mx. Okay, it means that wherever I see y, I write down mx, and on the numerator I have x times y, which is now x times mx divided by x squared plus mx squared. If you simplify this expression, you get m divided by 1 plus m squared. As you can see, the final expression has no x in it. It means that the limit of the function depends on m. You can plug in any number you like for your m, so you get multiple values for your limit of the function. It means that the limit doesn't exist. Or you can use the longer version. You can take different paths for your function and check to see if you have limit. Very well, the first path you can take is y equal to 0. Wherever you see y, you write down 0. F of x and 0 is equal to 0 divided by x squared, which is 0. What's the meaning of that? It means that as you walk along x-axis or y equal to 0, the limit of the function is getting closer and closer to 0. Let's check a different path, x equal to 0. Wherever you see x, you write down 0. F of 0 and y is equal to 0 divided by y squared, which is equal to 0. What's the meaning of that? Again, you get the limit of the function getting closer to 0 along the path y-axis. Okay, here you cannot conclude that the limit of the function is equal to 0. You have to check more paths. For example, suppose you take a different path, y equals to x. If I just substitute x for y into the function, my outcome is x squared divided by 2 times x squared, which is a half. So as you can see, if you walk along path y equals to x, the limit of the function is going to be a half. A half is different from 0, so it means that the function has no limit when x and y are getting closer and closer to the origin.